Hello, yeah. In this video of our machine learning using R series, I want to talk about boosting using the R package lightGBM. So lightGBM is another R package implementing boosting for gradient boosting machine. Okay, so we know GBM was implemented in the R package GBM. So here is a comparison between lightGBM and GBM. Okay, lightGBM uses leaf-wise tree growth, and GBM uses level-wise growth. And lightGBM is faster and more scalable due to histogram-based splits and advanced sampling. lightGBM supports categorical features and parallel GPU training, and GBM does not. GBM is simpler, slower, and best for smaller datasets or legacy code. lightGBM excels in large-scale applications and competitions. GBM is preferred for interpretability. So you can see the lightGBM is usually is good for a large data set and faster computing. So this is actually I'll show you it also has better accuracy as well. Okay. So let me walk you through this example. Set a random seed, create a data set. Now we want 500,000 observations, 100 variables. And this is the data set look like, the first 6 rows. Okay. So this is a pretty large data set. Okay. And then we need to install lightGBM, and the working R codes for installing lightGBM is posted here. It's commented out, but you can use this command to install it. Okay, so let's load it in. And also, the old RPack GBM is no longer working, so now it's a GBM3, and you have to use the remote package to install from GitHub by using this line of command to install GBM3 here. And after install that, just load it in, and then we create a training index, create a training data set, and test data set, etc. So first we just get the training data set here. Then we can fit the lightGBM model using the lgb.train function in the lightGBM package. So here we just use parameters equal to the objective equal to regression, maximum depth equal to 6, data equal to d-train, n rounds equal to 100. Okay. So you can see it converges pretty quickly, but we notice some warning messages. And this is just saying we need more better control for the hyperparameters. So here we reassign the parameters as a list, objective regression, number of leaves equals 31, and maximum depth to -1, no explicit depth limit, and then learning rate 0.05, and minimum data in leaf is 50. Okay, so once we set up that hyperparameters list, we can rerun this model training command. However, you notice I used the system.time function. I want to record how much time this model fitting will need. Okay, so let us run this model training. Okay, you can see the user 30.57, system 5.02, and elapsed 9.22. So the user is how much time will run on the CPUs on my computer, and system is how much time it run on the operating systems, and then the elapsed is the total time that's need. Okay, so you can see the user is 30.57 and elapsed is 9.22, and the elapsed the total time, that's total runtime, and you wonder why the user runtime is larger than the total elapsed runtime. This is because the job was run on multiple different CPUs, so that's why I have 30.57 user time. Okay. All right, and then we would train the model using the lightGBM, and we can use the GBM function in the GBM3 package using this line of command. So GBM regress on all the other predictors, and then on the training data set, we say number of trees is 100, interaction depth equal to 6, and shrinkage equal to 0.1. Okay. Okay, let's run that. Okay, I actually paused recording on my laptop, just waited out for this GBM model fitting process to complete. Now it's completed. We'll come back to that. So you can see now the system time function reported user is 249.01, systems 1.73, and elapsed as 252.81. So it took much longer than the light GBM took. So you can see the light GBM is much faster computationally. Okay. And also I'll show you we can assess the prediction accuracy of these two boosting machines, the light GBM and the traditional GBM. We can compare their root mean square error and the R square of the model. So let's set random seed, get the training and the test data set, grab the test data set predictors and test data set dependent variables, the response, and then we can generate a prediction using the lightGBM model, the lgb_model on the test data set. You can see it very fast. And then we want to generate the prediction for the model fitted by the traditional GBM. And for that, we need to do a bit of tweaking. First, I need to just given the number of tree used as 100. Otherwise, it's going to ask you to search for the optimal number of trees, which will trigger additional processes and time. So here I just say, okay, we'll just use 100. And then we can do the prediction model using the number of trees, and then we can generate the prediction. And then we write functions to calculate RMSE and R squared. And then let's get the test dataset response. And then we do the RMSE and the R squared. And then we just put them together here. You can see the RMSE for the light GBM is 1.1438. The RMSE from the GBM is 1.2795. So the RMSE from the light GBM is smaller. And R square of the light GBM is 0.6982. R square from the GBM is 0.6223. So the R square from light GBM is a little bit higher. Okay, so we have smaller prediction error and higher R-square values, and we have much faster computing speed from the lightGBM. Okay, so from this example, it gives you some sense about the superiority of lightGBM, especially on large data set. So just keep that in mind. You have a tool that you can use for large scale boosting. All right. And that's the purpose of this video. And thank you for watching. Please like our video and click on the notification and also subscribe to our learning channel. Thank you.